so if now let's begin our lecture today. So this lecture is really designed to have all of us to work together. So I want to go, we're going to practice a lot of problems. So I'm going to go for, what's your name again? Alex, your same name, so we can work on the problem together, okay? So basically we want to compute the partial derivatives. So this is really the very beginning of multivariable calculus, right? So there are two main pillars of calculus, derivatives and integration. So at least after this semester, you have to be able to do those two things, right? So I give you a function z is equal to f of xy. You should be able to do the partial derivative as well as the integration. Without being able to do this, you can call your whole semester total failure. Okay, so you have to be able to do this. So first, let's fix our notation. So this is the partial derivative. So I will say this is a partial derivative of a function f with respect to x evaluated at the point AB. Partial of f with respect to the variable x evaluated at the point AB. Okay? And there are very popular other notations you can use. For instance, people can also denote as partial f, partial x evaluated at AB. Or simply, you just write f subscription x evaluated at AB. All those three notations are acceptable here. Okay? And because we have two independent variables, if you have a partial derivative with respect to x, you also have a partial derivative with respect to y. Partial f, partial y evaluated at AB can also be written as partial f, partial y, AB, or simply f sub y at AB. Okay? So the notation for partial derivatives are as follows. The computation is extremely easy. Okay? The computation for taking partial derivatives is just the same as the single variable calculus. So instead of taking the rules, let's just look at the examples. Okay? So if I take the partial derivative with respect to x, I'm regarding the other independent variable as constant. Okay, I'm taking this function, partial derivative with respect to x, and regarding y as the constant. So taking the derivative is just the derivative of a single variable function. Okay, so when you are looking at a partial derivative with respect to x, this is the function, y is the constant, it's a function of a single variable x, so we're just taking the derivative of this function with respect to x. What do you get? 3y cubed. And a constant function taking the derivative is just equal to 0, all right? So taking a partial derivative in terms of computation is exactly the same as the rules of single variable calculus. So I will quickly review the rules of single variable calculus. So if I have two functions taking the derivative, we have the product rule says it equals f prime g plus f g prime, all right? We have a product rule, we also have a division rule. So the division, taking the derivative, we have g squared in the denominator, f prime g minus f g prime, okay? So as long as you realize this principle, computation is straightforward. So Evan, right? Yeah. Evan, so how do I compute the partial derivative with respect to y?
For that one?
Yeah, for that one.
Oh, okay, that'll be 9x y squared.
So x is the constant, y is the variable here. So I'm pulling out a 3 right here. So it's going to be 9x y squared. Okay. And this is the partial derivative with respect to x and y. And then if you want to evaluate at different points, partial f, partial x, evaluate, let's say at 1 and 2. So how do we do that? You just plug into the formula we have here. So this is the partial derivative with respect to x, evaluated at the point 1, 2. Of course, because the variables are in R2, so every point you have to have a pair of numbers. So we plug in this number, evaluate for this function, you get a 3 multiplied by 2 cubed. So what do you have? 24. And a partial derivative with respect to y evaluate 1, 2 is equal to 9 times 1 times 2 squared. So 36. Okay. See, these computations are very, very easy. Before I move on to the next gentleman, what's your name again? Ali. Ali. You do want to wonder. We compute these partial derivatives. We evaluate at this point. What does 24 actually mean, right? And what does 36 actually mean? You do want to ask yourself these questions. Computation is pretty easy, but also we wanted to translate this information of numbers into our understanding of the multivariable function. So I ask you this question. If I have a function involving only one variable, y is equal to f of x, I take a derivative of f, translating back into the graph of a function. So this is the function y equals f of x. Evaluated at a given point x equals a. Right? Evaluated at a given point x equals a. The partial derivative evaluated at this given point a, what does it mean?
Slope.
It is the slope of the tangent line. So the partial derivative should have similar property. If you have one single variable, I have only one derivative, and this derivative is talking about a tangent line, especially the slope of the tangent line. So what we want to do next is not only to compute the partial derivative, but also to give it a geometric meaning. What does it mean? Especially, for instance, we know if the slope is equal to 0, this tangent line has to be horizontal, right? So what does this partial derivatives, for instance, if I have a partial derivative with respect to s, evaluated at a given point is equal to 0. If I go to the graph, what does it tell me? So what is the graph of a two-variable function? Instead of a curve in R2, it's a surface in R3. So we have to translate every partial derivative information back onto the surface. What surface? I have a plane, I have pieces of part of the surface and so on. So we have to be able to do this. So next, I still want to practice our computation on the partial derivatives. So Ellie, so I'm looking at a function fxy is equal to x cosine xy. So partial f partial x is equal to
x sine.
So this is a product of two functions involving x, okay, right? So you want to use a product right here. So what is it?
X times sine.
So x times sine
X of y.
xy.
Was.
And then y is the coefficient. So you're taking the derivative of this whole thing, this factor with respect to x, am I right?
Yeah.
So times y as well, right? Remember, the principle is if you're taking derivative with respect to x, y is just a number. You can essentially regard it as a number. And then plus 1 times cosine xy. Very good. So this is our application of product rule. So it's xy sine xy plus cosine xy. So next, partial f, partial y. What do you got? Oh, question for Ella.
Won't the first time be negative?
Oh, sorry. Yeah, it should be a negative sign right here. Yes, it should be a negative sign. So I will take the blame here. So partial f, partial y, what do you got? X becomes the constant, right? So it's not even, you don't even need to use the product rule anymore. Are with me? So x is essentially a number, right? So I'm taking the derivative with respect to y.
sign, negative sign,
negative sign,
and xy
xy,
times y.
times, but I'm taking the derivative with respect to y, so x is supposed to be the coefficient, right? X is the constant, so I still have to keep my constant in the front, right? And then going inside, which is essentially applying chain rule, all right? Chain rule, I'm applying derivative inside with respect to y, I still have to get a x as the coefficient. Now with me? So this is going to be minus x squared sine xy. One way, if you do not see how to take the partial derivative, you can practice by replacing x by numbers. For instance, if I ask you what is the derivative df dy, where my f is just equal to, say, 2 cosine 2y. All right? Essentially, you're doing the same thing. If you're taking the derivative of this function with respect to y, 2 is the constant. All right? You're keeping the 2, you have a minus sine 2y, and then going inside, you have another 2 coming out. All right? Which, when you are doing partial derivative, the only thing you're doing here is x plays the rule as the constant here. Now with me? Okay, questions? You have to at least be able to do derivatives after you finish this semester. Otherwise, it's just so embarrassing to say even take calculus class. So how about I evaluate, for instance, at 0. If x and y are both equal to 0, what do you got here? 0, and 1. So the partial derivative with respect to x evaluated at the origin is equal to 1. And the partial derivative evaluated at y is equal to, I'm sorry, 0, 0 is going to be equal to 0. So you have a slope of something equals 1 and slope of something equals 0. After we practice a couple more, I will briefly discuss what these numbers actually tell us. So Alan and Abby. I'm sorry I'm taking more time to remember all the guy's name. So next one, let's look at an example where we might be able to use the portion rule. 5s minus 4t divided by 4s plus t. So even though throughout the semester our choice of letters as the independent variables are mostly x, y, or z, but these letters are just very arbitrary. You can choose whatever letter you want. You can use S, T, W, X, Y, Z, A, B, C, whatever you want to use. So this is a function involving S and T. So I want to take the partial derivative with respect to x. This is only a review or an application of single variable calculus in the two variable case. All right? So this is your turn. What's your name again? Oh yeah, yeah. So that's your. So partial f, partial s. What do we have?
4s plus t.
So 4s plus t as the denominator. You want to square it.
Yeah, and the 4s plus t
So I want to take the derivative of the numerator with respect to s. Right. So it's 5 multiplied by the denominator, all right? So when I use the quotient rule, I'm having derivative of the numerator multiplied by the denominator minus f multiplied by the derivative of the denominator, all right? Let's keep that rule in place. So it's going to be 4s plus t minus derivative of 4 multiplied by 5s minus 4. Okay, so this is what we have. And then we can do a bit of simplification. It's going to be 4s plus t squared. We have 20s plus 5t minus 20s plus 16. All right? So these get canceled. So we have 21t divided by 4s plus t squared. Yes? Am I making any mistake? These are all simple numbers, so hopefully there's nothing going on here. So I want to practice partial f partial t here. Still u. So let's compute partial derivative with respect to t.
4s plus t squared.
So 4s plus t squared, that's still the same.
Negative 4.
So I want to take the derivative with respect to t, am I right? So I need to take the derivative of the denominator, the numerator with respect to t. So it's minus 4 multiplied by 4s plus t, then minus. What do you got? Just 1. So it's just the denominator with respect to t, so it's going to be 1 multiplied by 5s minus 4t, okay? And then we can do a bit of simplification. Put this together, so 4s plus t squared, I have a minus 16s minus 4t minus 5s plus 4t. So I'm gonna get these canceled. So it's gonna be minus 21s divided by 4s plus t squared. Okay, so this is our answer for this fraction. Okay, again, these computations are pretty easy. It's just a matter of getting used to it. Okay, so there are so many different two-variable functions we can generate. So you can practice your own skill.